Is it okay? Can you hear me in the back side? Yeah. So I need some hands-free for demos. So a little bit about power electronics. I guess this is also your line of business because you're using drives for the automotive electrical motor thing. Yeah. Well, this is typically an industrial one, UPS system, a switch mode power supply that in case of a power cut will be supplied by the battery and then provides the power supply. Or a motor drive, a three-phase industrial motor. I guess in automotive it's DC motors or
yes.
No three-phase?
Both.
Both. Okay, so anyway, it doesn't matter because what's inside is actually the same. So it's a switch mode power supply. So you've got the rectifier here, some DC thing, and in case of your automotive thing, you've got the battery here, and then some switch mode power supply, and then hopefully some filters on the outside, the output and the input. Because one of the questions was, when you put this drive on the battery of the car, then anything on the same bus will get some noise from this device to the, well, sensitive electronics. So you need these filters. So the answer is you need filters on the drive side. Actually what's happening here is the square wave thing that Fritz has showed you. You've got all square waves there and all the coupling effects. And what I want to show you is the capacitive effect here in the motor. So we've got the rectifier here, you've got some harmonics, but that's not your problem, I think. We've got the capacitance here. So between the winding and the motor casing, I've got an industrial motor here. There's a winding inside, and it actually sees the capacitance to the aluminium casing, which is earthed with this earth wire. So we've got the square wave thing here, and then the capacitance, and then actually there's a return circuit here. So we get the same type of disturbance currents that Fritz has shown you with the square wave generator. So the VDT, the steepness of the voltage, as a function of time, is well around 3 kV per microsecond. That's actually what you buy in terms of semiconductors. That's what you can get on the market. And of course, the faster you have this switching thing here, the less dissipation you will get in the transistors. So the keyword in the last decades actually was high efficiency rather than EMC. So we had lots of problems in industry because of these motor drives. Because we used very steep voltage switch mode power supplies, and then with this capacitance you get this common mode current. And of course we use some screening. So this is the circuit what I've got here. I've got my variable speed drive, the box here. I've got my electrical motor, which is on the field side. And I've got a screened cable. So there's some braiding actually around the cable. It actually has 3 conductors, so 3 phases going to the winding and then capacitance to the earth. So this makes the common mode loop. And we can make an estimate by using this capacitance, 1 nanofarad, we can actually measure on motor terminals. And then with the VDT, we get some number of amps, peak value, of current going this way, back to the source, always back to the source. So what's the idea of using the screened cable? Because what I'm doing now, I will first show you the effect without the screening effect. So I've got the cable braiding, the shield terminated here with a gland. So it is a metallic connection between the shield and the motor casing. But at this end here, it's hanging loose, so there's no shield connection. And then in the second stage I will connect the screen. But any idea what happens if we connect the screen at both ends?
You get another connection, another loop.
So you get a second loop, yeah. So, and Fritz explained about Lenz's law, and of course it's more energy to go this way, far away from the cable. So through the neighbor's circuitry. It's easier to go back on the screen, of course. Let's see what happens. So I've got two measurements. I will actually show you the voltage. So when I switch on the variable speed drive, and I've got two channels. Well, it's actually like this, yeah, but I enlarge this picture, and I will show like this. So it's actually the same what you saw in Fritz's demo. Square wave in a few hundred volts, so 300 volts going up and down. And the current, which I'm measuring here with the clamp, that shows you values of, let's see, well, 6.5 amp, peak to peak. So it's more or less what we can calculate. I've got a little bit more because the cable also has some capacitance. It's not just the motor. Well, this gives you a common mode loop, and it's producing noise. There's some other noise here, of course. And well, the frequency range, if we look a little bit closer, I will switch off the voltage. So this is a typical ring wave, 1 microsecond. So it's 1 megahertz. So the medium wave frequency band is disturbed. That's what you can hear on the radio. But actually we've got quite a high current. So we have to shield the cable. That's what I'm going to do. So I will show you what happens if I connect the shield at both ends. So I'm going to connect the cable shield to the variable speed drive, or the earthing system. There it is. It's impressive, isn't it? Lots of, well, factor of 2, maybe 3. But is this the preferred practice? Is this good? Or no. Probably. Should be, well, it should be nil. Yeah? It should be 0. No leakage current. And actually what goes wrong here is the, well, this one is a black wire, you use the red one. Yeah. Yeah. But if I produce a coil, there are some bad contact. If I make it, should be a bad contact. I need a good curve somewhere. Right. So if I make it flat, it's better than the big loop. So here you see the effect of the pigtail. And actually it should be a very short, well actually it should be what we call a gland. Yeah, but what I'm going to use is a braided thing. So it is good for high frequencies. And I'm actually going to connect it like this. Lots of bad contacts here. Sorry. I connect the screen against the box.